15.7 Regarding regression coefficients. Before moving on to discuss the assumptions underlying linear regression and what you can do to check if they're being met, there's two more topics I want to briefly discuss, both of which relate to the regression coefficients. The first thing to talk about is calculating confidence intervals for the coefficients. After that, I'll discuss the somewhat murky question of how to determine which of predictors is most important. 15.7.1 Confidence intervals for the coefficients. Like any population parameter, the regression coefficients beta cannot be estimated with complete precision from a sample of data. That's part of why we need hypothesis tests. Given this, it's quite useful to be able to report confidence intervals that capture our uncertainty about the true value of beta. This is especially useful when the research question focuses heavily on an attempt to find out how strongly variable X is related to variable Y, since in those situations the interest is primarily in the regression weight beta. Fortunately, confidence intervals for the regression weights can be constructed in the usual fashion. Ci beta equals beta hat plus minus bracket T sub crit times capital SE beta hat and bracket, where SE beta hat is the standard error of the regression coefficient and T sub crit is the relevant critical value of the appropriate T distribution. For instance, if it's a 95% confidence interval that we want, then the critical value is the 97.5th quantile of a T distribution with n minus k minus 1 degrees of freedom. In other words, this is basically the same approach to calculating confidence intervals that we've used throughout. To do this in R, we can use the confint function. The arguments to this function are object, the regression model, LM object, for which confidence intervals are required, parm, a vector indicating which coefficients we should calculate intervals for. This can be either a vector of numbers or, more usefully, a character vector containing variable names. By default, all coefficients are included, so usually you don't bother specifying this argument. Level, a number indicating the confidence level that should be used. As is usually the case, the default value is 0.95, so you wouldn't usually need to specify this argument. So, suppose I want 99% confidence intervals for the coefficients in the regression 2 model. I could do this using the following command. Confint bracket object equals regression period 2, comma, level equals 0.99 and bracket. Then the output you get is for the intercept, for Dan sleep, and for baby sleep. And then the two columns are 0.5% and 99.5%, and then you get the confidence intervals for each variable. Like, for example, for intercept, the 0.5% confidence interval is 117.98, and the 99.5% confidence interval is 133.96. Simple enough. 15.7.2 Calculating standardized regression coefficients. One more thing that you might want to do is to calculate standardized regression coefficients, often denoted capital beta. The rationale behind standardized coefficients goes like this. In a lot of situations, your variables are on fundamentally different scales. Suppose, for example, my regression model aims to predict people's IQ scores using their educational attainment, number of years of education, and their income as predictors. Obviously, educational attainment and income are not on the same scales. The number of years of schooling can only vary by tens of years, whereas income would vary by $10,000s of dollars or more. The units of measurement have a big influence on the regression coefficients. The beta, small beta coefficients only make sense when interpreted in light of the units, both of the predictor variables and the outcome variable. This makes it very difficult to compare the coefficients of different predictors. Yet there are situations where you really do want to make comparisons between different coefficients. specifically, you might want some kind of standard measure of which predictors have the strongest relationship to the outcome. This is what standardized coefficients aim to do. The basic idea is quite simple. The standardized coefficients are the coefficients that you would have obtained if you'd converted all the variables to z-scores before running the regression. The idea here is that by converting all the predictors to z-scores, they all go into the regression on the same scale, thereby removing the problem of having variables on different scales. Regardless of what the original variables were, a capital beta value of 1 means that an increase in the predictor of 1 standard deviation will produce a corresponding 1 standard deviation increase in the outcome variable. Therefore, if variable A has a larger absolute value of capital beta than variable B, it is deemed to have a stronger relationship with the outcome. Or at least that's the idea. It's worth being a little cautious here, since this does rely very heavily on the assumption that a 1 standard deviation change is fundamentally the same kind of thing for all variables. It's not always obvious that this is true. Leaving aside the interpretation issues, let's look at how it's calculated. What you could do is standardize all the variables yourself and then run a regression, but there's a much simpler way to do it. As it turns out, the capital beta coefficient for predictor x and outcome y has a very simple formula, namely capital beta sub x equals beta sub x times sigma sub x divided by sigma sub y, where sigma sub x is the standard deviation of the predictor and sigma sub y is the standard deviation of the outcome variable y. This makes matters a lot simpler. To make things even simpler, the LSR package includes a function standard coefs that computes the capital B coefficients. So you can input standard coefs bracket regression dot to end bracket. Okay, which will output the lowercase beta value and then what they call the beta value, which is different. This clearly shows that the Dan sleep variable has a much stronger effect than the baby sleep variable. However, this is a perfect example of a situation where it would probably make sense to use the original coefficients, small beta, rather than the standardized coefficients, capital beta. After all, my sleep and the baby's sleep are already on the same scale, number of hours slept. Why complicate matters by converting these to z-scores?